Welcome to my AI evolution simulator written entirely in JavaScript. So in this simulation, instead of using predators and prey to simulate evolution, we're using cars and obstacles on the road. These cars on the screen are learning from scratch how to survive. They start off completely clueless, but generation after generation, they slightly improve, and eventually they begin to show signs of intelligence. Each car on the screen is powered by a tiny neural network. And over time, these networks evolve by selecting the most successful ones, cloning them, and slightly mutating their internal weights. An important thing to note is that there is no pre-written logic for dodging obstacles. These cars are simply learning from trial and error. Here's how the evolutionary algorithm works. At the beginning of each generation, we spawn an initial population of cars. As the simulation runs, we track which cars go the farthest, and at the end of that generation, we select the cars that perform the best. We take these top performers or parents and we clone them. After we clone them, we slightly mutate their internal weights, and these new children cars are used to populate the next generation of cars. The whole idea is that if something works well, then maybe small changes will make it perform even better. Over time, the bad drivers get weeded out and the good drivers become experts. So, how do our cars actually see the world? Well, each car outputs 5 different rays, which are kind of like sensors at different angles. This is actually the ray class, which keeps track of important data points surrounding each individual ray, as well as different methods that help us perform useful calculations. For example, I am using this cast method to compute each ray's intersection with the closest obstacle, if there is any, and it updates the endpoint and the hit data. These 5 ray values are then normalized and fed into a really simple neural network with just 5 inputs, a few hidden neurons, and one output. That one output determines how quickly the car moves either left or right. As you can see in this constructor for the neural network, we are creating the architecture for our neural network. Here you can see we have our input size, which is 5 for each ray. We have a hidden layer with 3 neurons, a hidden layer with 2 neurons, and an output size of 1. This method right here is the predict method. It actually takes in the inputs, does a forward feed through our neural network, and it outputs the final value in the last neuron of our network. This output is between 1 and -1, and it represents horizontal movement. This right here is the animation loop within the main program, and it is what is being called constantly to update variables associated with cars, as well as draw those cars and obstacles to the screen. One of my absolute favorite things about this simulation is that you can manually mess around with the different parameters associated with the simulation and instantly see how it affects how far and how successful your cars are. So right here, you can change the number of obstacles that will be on the screen at any given time. You can select the number of cars that are a part of an initial population. So this means that each generation, 40 cars will be spawned into the simulation. This is your parent count, which basically tells you how many top performers you're going to select from each generation for reproduction. Your mutation rate tells you the percent chance that a given weight or bias in your neural network will actually be mutated. So we essentially loop through every weight and every bias. And for example, right here, there would be a 35% chance that that bias would get updated or changed randomly. Finally, you have your mutation magnitude, which tells you if a weight does get changed, this is the max that it could possibly change by. And in reality, it will change somewhere between this value and negative this value. So somewhere between negative zero point 0.2 and positive zero point 0.2. Another one of my favorite things about this simulation is the stats graph. So this graph shows you in real time how your cars are performing to previous generations. So as you can see, our first generation of this simulation started off around 600. We slowly climbed up to over 2,000 for an average distance. We had a little bit of a dip, which is bound to happen because these cars are having random mutations done to them. So not every generation is going to be better than the next. Then you can see in the fifth generation, we improved quite a bit. I will also add some other graphs that I've collected to this screen right here so you can see what some of them might look like. If you're interested, I have created a web page for this simulation, so I'll leave the link in the description of this video. And if you're interested in playing with the parameters and seeing what creates successful cars, then I encourage you to go and play around with that. I'll also leave the link to my GitHub repository for this project, just in case you're interested in diving into the code behind how all of this works.